All right, well, I think we can get started now. We'll probably have a few more folks joining us throughout, but I want to respect everyone's time that's here on time. So thanks for joining today. I'm just about to hand it over to Lisa King for the first part of the session, but just wanted to mention to everyone just to be aware that we are recording today's session. We are planning to post it to YouTube, the presentation portion of the day or of today's session. We are going to have some breakout sessions where we really want people to engage and share their opinions, and we won't be sharing that part. We're going to edit that out and we will record it for our own purposes so we can review and make sure we capture everyone's comments, but the discussion part will not be shared to YouTube. So I just wanted to make that clear for everyone. So I will hand it over to Lisa to kick us off.
Okay, welcome everybody to our third Materials Matter workshop session. This is about two really important studies that we have underway. One has been published, so you'll hear about it, but they're both to establish embodied carbon benchmarks for buildings in Ontario as a way to set targets in policy and in standards. Next slide, Ryan. And this is just an overview of our agenda today. So you're going to hear some really wonderful educational presentations at the beginning. You know, some of the basics of what embodied carbon is, why it's important, and then hear about the two studies and the key findings and outcomes of those, both of which were funded by the Atmospheric Fund, so we're really appreciative of that. Then we'll have a quick break, and then the important part to get your input on you know, how we might enable action on this issue in the work that we all do in this particular industry. So hopefully we've got a good representation from contractors and builders today and consultants. And then we'll wrap up by 12:45. That's our target timeline. And last time we were able to stay on track, so I think we'll be able to today. And these are the few speakers starting out at the beginning. And then we do have some pop-out speakers, surprise speakers later too for you. But I'm Lisa King. I'm with the City Planning Division. I'm a senior planner there, and I oversee the Toronto Green Standard that many of you will be familiar with. And Ryan Zizzo is the CEO of Mantle Developments, who's one of the primary consultants on the Part 3 large building study, alongside Kelly Alvarez-Doran, who also is adjunct professor at University of Toronto, doing a really interesting design studio there called Half Climate Design, and working on this study for big buildings. And then Chris Magwood, who has led the Part 9 low-rise study, a benchmarking study, and you'll be hearing from him on the findings too. So just as a quick context piece to the presentations, the reason that we're doing this work is to inform the next Toronto Green Standard. So the TGS are environmental performance standards for new construction in Toronto since 2010. There are 5 categories of performance measures, and something like embodied emissions falls under the energy and resiliency section. There are 3 different standards and required and voluntary tiers, and it addresses and incorporates our zero emissions buildings framework from 2018. Next slide. And one of the key aspects of that zero emissions building framework is that, you know, buildings account for over half of the emissions in Toronto. And so we have a stepped framework, a set of performance tiers out to, originally it was 2030. And that time frame was shortened in December of last year by City Council as part of the Net Zero 2040 citywide strategy that was adopted. So Council asked us to shorten the time frame of implementation so that what is now the new Tier 3 will be the Tier 1 of 2028 in terms of the energy targets, the energy and emissions targets we have for buildings. And that Tier 1 of 2028 or Tier 3 under TGS version 4 is very low emissions. As you know, it's sort of a near emissions level. So it's very high performance, and we want to try to get through these steps and follow through on these timelines and implement them as a really important part of us achieving our citywide GHG reduction targets. Next slide. So the 2 studies, again, funded by the Atmospheric Fund. So one is for the Part 3 large buildings, looking at benchmarks, so looking at real projects across Ontario and to see where they're landing in terms of the current kind of construction practices and how we might set targets. And again, for the Part 9 small low-rise buildings, again, another Ontario-wide study that you're going to hear about. And we want to really hear from you today on what we're thinking of, what you hear, first of all, in the presentations, any of your reactions to that, what you think might be some of the key challenges. But the idea is that we work towards a primer. What's being called a policy primer is a deliverable for the large building study by July. And that's something that the consultants are working on right now, just getting started on. And all of this workshop feedback is feeding into that document so that it can be really useful for all GTHA municipalities in trying to address this issue as part of their climate change plans. And with that, I think I will pass things over to our first speaker. That's Ryan Zizzo from Mantle.
Great. Thank you, Lisa, for that. And just to let folks know who might have joined after my initial announcement, we are recording the session. It will be posted on YouTube, but we won't be recording the discussion section. Sorry, we won't be sharing the discussion section. We're going to edit that part out. So feel free to speak freely when we have our discussions. So I'm going to be doing a bit of a 101. What do we mean when we talk about embodied carbon or life cycle assessment? And basically, I like to use this graph to set the stage. The sections that are shaded in blue and the bubbles, you see the CO2 bubbles in blue, those are all the emissions. Those represent the emissions associated with our construction processes that aren't currently being regulated or measured or reported when we're only focusing on operational energy. Operational energy is basically from energy use, energy efficient, energy consumed of our built environment. And we're doing a good job of regulating that with the Ontario Building Code and things like the Toronto Green Standard for the last 4 versions of it. But none of those documents, except for the newest version of the TGS, have looked at embodied carbon. So we're talking about where materials are being manufactured, transported to the construction site, the actual installation processes themselves. So think of all of those excavation trucks and cranes and diesel trucks on construction sites. The use phase of a building, meaning when we are replacing major material parts of the building, like windows or redoing the roof in 20 or 30 years, or doing a major renovation, all the materials associated with those are use phase embodied emissions. And then there's finally end of life emissions associated with deconstruction, disassembly, demolition, and transportation and final waste processes. So it's really the sum of all of those activities together is what we're referring to when we say embodied carbon or embodied emissions. And all of this is calculated using something called a life cycle assessment, or an LCA. That's the approach that is taken to do this type of analysis. So you might hear those terms interchangeably, but LCA is really the methodology, the approach, and embodied carbon or embodied emissions is the output of that study. So why are we talking about this? Why is this an issue? Well, a lot of folks know buildings are responsible for a large amount of emissions, but they typically, when people talk about that, they're really only talking about operating the buildings, the operational carbon. And you can see on this graph of global emissions, the red slice here represents the operational carbon of running our buildings. What's less understood or talked about or reported even is the emissions associated with constructing the buildings, putting them up in the first place. And that's fully 11% of global emissions, which is pretty shocking to most people. They don't, haven't come across this data before. And when you drive down into that, a full 8% of global emissions is just due to concrete and cement. And the good news is there is quite a lot of low-hanging fruit in all of these materials, concrete, even wood and glass, insulation. We'll get into some of the solutions later, but there's a lot we can do as designers and procurers and developers, building owners, the people on this call, to greatly reduce the carbon impact of our buildings by asking the right questions from our suppliers. So this image, which is from the World Green Building Council's report called Bringing Embodied Carbon Upfront, which is a great resource. I recommend people to check out if they want to learn more. It shows the different life cycle stages that are typically included in a whole building life cycle assessment. And as you start getting more familiar with these types of studies, you'll see these codes. Like people will say that these are results from A1 to A5, or from B1 to B5, but excluding B6. So I just wanted to show this to explain what those numbers and codes mean. They are all related to specific life cycle phases within a building's life cycle, as you can see here. I won't go through all of them, but just to show that the green box here, the embodied carbon, you can see it does not include the B6, which is the operational energy use. That's because that's typically already being managed and reported and optimized through energy efficiency requirements. So basically, we like to think of embodied carbon as everything other than the operational energy and water use of the building. I'll also note there is a D phase, which is referred to as the beyond life cycle phase. And this is all about recycle and reuse of materials for the next building. Typically, if D is included, it's reported separately and not aggregated into the other results. The other thing I'll point out here is A1 to A5 is referred to as upfront carbon. So this really means the carbon pre-occupancy. So A5 is the construction process itself. So this is everything where the raw materials come from, manufacture, transportation to site, and installation at the site. But before people move in, that's when we shift into the use phase. And we've seen that the embodied carbon, I'm finished my sentence here. The embodied carbon for the upfront is actually the vast majority of all of the carbon of the building. It's typically over 75%, maybe even 80% or above. So there's been a movement of people focusing more on the upfront carbon because it's the biggest source of emissions and it's the stuff that we can immediately deal with in procurement. I like to use this graphic to show why this is becoming increasingly important with time. The top part of the graph is typical carbon profile of a building over a typical lifespan, say 60 years of a building is in use. And this is showing the cumulative carbon in the atmosphere at any given time. So in year one, before anyone moves in or before the lights go on, all the carbon is from the embodied, right? It's from getting the materials, producing them, getting them to site, putting the building up. But every year we start heating and cooling and ventilating the building and more energy is used and the emissions from that energy use is going into the atmosphere. By the time we get to the end of the life, 60 years, for a typical building of the past, there was significantly more operating carbon in the atmosphere than there was embodied carbon. And that's because our buildings were not very efficient in the past and because our energy grids were quite dirty. But neither of those things are really true anymore, and they're becoming less and less true every day as new construction is continually being more energy efficient because of things like the building code and Toronto Green Standard, and also because we're decarbonizing our energy systems with things like adding solar panels, getting rid of coal, more wind turbines, and even injecting renewable natural gas into the system. So a new building today uses significantly less energy, and the energy it does use is significantly less carbon than buildings of the past. And that's why the situation has shifted to something closer to the bottom of the slide here, where operating carbon for new high efficient buildings is actually not vastly larger than embodied, but it's actually of about the same scale. And the relative scale depends on the region and the electrical grid and the building and the climate and a whole bunch of other things. But this is the trend we're seeing, where embodied carbon is becoming a much more significant piece of the carbon pie. And things get even more interesting when we think about shorter timeframes. For anyone that's been following the UN reports on this stuff, the IPCC, Intergovernmental Panel on Climate Change, we've been hearing warnings that we have 10 years or less now, a window of action to substantially reduce our emissions, or else positive feedback loops are going to kick in and we won't be able to control climate change. So when we look at this new reality of high efficiency buildings in a low carbon environment, a low carbon energy environment in shorter timeframes, it's actually the complete opposite situation as what we used to see, where previously operating carbon was dominating. In this new reality, embodied carbon is really the vast majority of the emissions that we need to be dealing with when we're talking about new construction. So that slide was, demonstrative, illustrative in purpose. This is actual real data. This is from an assessment that we did at Mantle Developments for the Government of Ontario on a confidential LEED certified building, a large government institutional building. And we found, and this was actual operating energy use because the building had been in operations for a couple of years, and we just extended that out, saying, assuming that the amount they were using today or in a given year would be the same over the future years. But we found that the embodied carbon, the blue part here, was, a very significant piece of the total carbon over the life cycle, and the dominant piece of the carbon life cycle. When we look at we used a 12-year window in this range, or in this study. The other thing I'll point out here is that the red dotted line, that's the carbon just from the concrete in the structure. So again, massive impact here from a single material, and a lot we can do to drive this significantly down, which we'll talk about later. So the first thing that we want to start doing to manage this is to ask for better data. What's the carbon footprint of your building material? And a way to do this is by asking for something called an environmental product declaration, or an EPD. I like to think of this as a nutritional label for construction materials. When we go to the store, it's actually illegal to buy something or to sell something that someone's going to eat if you don't tell them what's in it, if we don't have proper disclosure documentation. So why aren't we having that same logic when we talk about the materials that we're producing and putting things into the atmosphere with? So just like a nutritional label, an EPD has a whole bunch of data that you might not need to look at every little piece of it. And sometimes it can be overwhelming by all the numbers in them in the document. But just to show you here, there's typically a few key things you want to look at. One would be the declared unit. On a nutritional label, we call that a serving size. So on this example from a rebar EPD, these results are per metric ton of rebar. And maybe we want to optimize for fat or cholesterol or whatever the one or two key things we want to look for. On the label, maybe it's fat. On our EPD, it's global warming potential, or it might say GWP, which is just an acronym for that. And that's really the same thing as embodied carbon. There's kind of a lot of different terms for the similar thing, because this is an industry that is still not super consistent, unfortunately, but this is one of the reasons why we're hoping you guys learn some of these new terminologies and acronyms today. So in your APD, look for the GWP, look for the global warming potential, and you can see here the A1 to A3 is also reported here, which we talked about earlier. These are the different life cycle phases. So one thing to really to drive home is that there's different types of EPDs, or different scopes or scales of EPDs. So it's very common to have some EPDs that are done at the industry average level. So we call this a generic or an industry average EPD. And the two EPDs at the top of my screen here are examples of this for the Canadian cement and concrete industry. One is an industry average for Canadian cement. One is industry average for Canadian ready-mix concrete. So the folks that put these EPDs together, the industry associations, they went out and got data for all of their suppliers and did a weighted average depending on what province they were in and how much they produced. And this is an average for their industry. But that's not really super useful if we're trying to calculate the real carbon from the product that I ordered on my building, that's manufactured down the street. I want to know the data for that building, not for the whole industry across Canada. So to get that specific level of data, what we want to ask for is something called a facility-specific EPD, or a product-specific EPD. And this is for a specific given single manufacturer location. And you can see this one on the bottom of my screen here says, for Permacon, says this is a lightweight CMU block from the Milton plant in Ontario. So this is a specific location, which would be really useful to know if you want to purchase the materials from that location. I'm not going to get into all the details on this slide, but this is just to show you the breadth of policies that are already being rolled out across Canada, the US, and globally on this topic. In Canada, both Toronto and Edmonton now are requiring embodied carbon calculations for all city-owned buildings. The federal government has something called the Greening Government Strategy that has recently been introduced that requires reporting on structural materials as of this year for major projects, and a 30% reduction by 2025. The city of Vancouver has similar requirements that they are rolling out, and even Waterfront Toronto has specific requirements for projects on the waterfront that they must report their embodied carbon as well. There's a whole host of other policies in the US and globally, but the key thing I'll mention is what's called buy clean. That's kind of the terminology that's been sticking south of the border. And there's examples like Buy Clean California, and other states have buy clean policies of their own, which is really about limiting purchase of the state. When the state is doing procurement, they need to buy materials that are a low carbon version of the material. And there is a motion both north and south of the border to have federal buy clean policies being rolled out. Just to quickly mention, there are tools that can be used, databases and free tools, including one-click LCA, Athena, EC3, Tally. There's actually a new one, Beam, that I don't think we didn't update this slide, unfortunately, just thinking of that, but Chris Magwood, who will be speaking later, and his team released a new one called Beam for low-rise construction. So there's a whole host of tools that are already available on the market, free to use, that can help folks manage this issue. And I wanted to just quickly have a few slides here to show that this assessment is not a one and done thing. This is really part of the design process that needs to be integrated throughout design, because there's different solutions and information that we gather at each phase. So at schematic design, we can think about things like reducing the underground parking. What's the massing going to be, and what's the major material type going to be? Is this going to be a wood building or a concrete building or a steel building? These are the decisions that if we wait past schematic design, it's too late to inform them. When we get into the detailed design and design development, we can have a more robust understanding of the layouts and the walls and the partitions, and doing optimizations that are much more granular than we could have done at the previous stage at schematic. And then when we get into procurement and construction, this is where we start thinking about the material properties themselves. So what type of a concrete? What are the ingredients in it? What type of a steel product? Where are the suppliers? Where are we shipping it from? So as you can see, that's not something we could answer at schematic, but it's definitely something that we would need to understand if we want to minimize our carbon fully. And then finally, at the end of life of a building, once construction is done, during the use of the building, we can update our model for a final as-built assessment, because as everyone on this call knows, there's often many change orders throughout the construction process, and the issued for construction drawings aren't really indicative of the final result. So if we want to have a true final value, we can do it at use or at post-construction, and we can even use that value we calculate to go and purchase carbon offsets or removals to claim a truly net zero building. So a few real quick best practices. Number one is just to ask your suppliers, is there a lower carbon option? What is the carbon footprint? Do you have an EPD? These are the questions we need to start asking on every project. We found that the tallest buildings actually have a higher intensity of embodied carbon due to additional underground structure and foundations. In terms of material specific solutions for concrete, there's a few things we can do. One is use Portland limestone cement, which is a 10% lower carbon impact. It's been approved by all the regulators in Canada. It's cost neutral. It doesn't impact your schedule. So it's really one of those no-brainers that really everyone should be using Portland limestone cement by default. We also want to maximize our SCMs. Most mixes have around 5 to 10% SCMs. We can push that significantly higher, closer to 30 or 40%. Definitely want to talk to your concrete supplier and your structural engineers about this, but tell them let's optimize let's maximize our SCMs to reduce our carbon footprint. And then finally, we can put longer curing times for elements that don't require early strength. Elements that require early strength are suspended slabs and beams. Basically, all the other concrete in our building, we don't need 28-day curing time. Slab on grade, walls, foundations, columns, all of those materials, which is probably the majority of the concrete in your building, it can cure in 56 days. It can reach its strength, or even 91 days for some of the elements, which allows for significantly less cement to be used and a significant reduction in the carbon footprint. For steel, we want to ask for North American steel with high recycled content. For wood, we want to ask it to be from a certified forest. So ideally it's certified wood to make sure that there is replanting going on and there's proper reforestation and ecosystem management. And in terms of the construction site itself, we can have electric vehicles. We can use electric vehicle delivery where possible. We can have biofuels. There's examples in Europe of zero carbon construction sites where they're not, instead of using diesel, they're requiring equipment that plugs into the low carbon grid that we have that we're able to use in Ontario. So there's a lot we can do across the entire value chain. Finally, I just wanted to mention that even though embodied carbon is a new area and it gives us a much broader look at the carbon footprint of our buildings, most embodied carbon assessments or LCA assessments, if they're following the LEED approach, which most people are, it doesn't actually include everything of a building. It includes the structure and the footings and the envelope rather. It doesn't include things like mechanical, electrical, elevators, parking lots, excavation. So there's a whole host of things that even if you are looking at a life cycle assessment of the building, it's probably not the full carbon picture. It's probably the majority of the carbon, but there's also more things that we need to do as an industry to ask for better data and be more holistic in the future and have a full picture of our carbon. So I'm going to hand it over to Kelly, and looking forward to discussing all with you during the breakouts.
Great, thank you, Ryan. And so I'm gonna cover basically how this theory is put into practice and where embodied carbon currently lives in our buildings, and how we have been tracking it through the TAF study and this part 3 study. So we've the TAF project overview. It's the first initiative in the region to collect and compare life cycle assessments for part 3 buildings. It includes a range we'll see between commercial, industrial, and forms of residential. We've also, I think, had the opportunity to work with two projects from the City of Toronto that are currently in development to see, what policy, how it might affect projects, but also where we can make some immediate reductions. And now we're taking this and the 4 workshops, this is the 3rd of them, to inform finally a recommendation for future policy informing the green standards. And I think beyond this, I think the bigger picture here is how to educate and engage the industry on this issue. So, this workshop and some of the work we've been doing, trying to get everybody thinking about this and frankly, making it a part of everyday practice. Next slide, please. So here are the findings we had. We have 52 projects that came back. 15 were from my research studio at the University of Toronto. And I think what you're seeing across part 3 is, the things that when I look at these statistics, I'm encouraged by them, that there's a pretty tight grouping of data in that 20th to 80th percentile within the types that the mixed use, the taller buildings, kind of over 5 stories, and the commercial and institutional other buildings is largely institutional and industrial, that they're grouped and they're all below 500 kilogram carbon equivalent per square meter, which is in keeping with what we've seen, in Europe and other parts of the world. So that means the data is pretty tight, that the grouping's fairly robust, and that it's in line with what we'd want to see. Also, I think useful to think that the multi-unit residential, it's significantly less. It's under 4 stories going to stick frame. There's certainly reductions there. Next slide. The majority of this life cycle emission is kind of outlined just now by Ryan. It's upfront. It's the cradle to gate emissions. It's all about how we're sourcing and making our construction materials. You can see even in the construction sites that are fully electrified, very little of the emissions are happening on site. It's really about how materials are being made, how they're being shipped across the world to Toronto, how they're being brought to ultimately the project site. Next, please. And here's where it lives in our buildings. So you can see, the majority is in walls and floors, and that's, it's kind of easy to understand that between beams, columns, forms, and foundations, those first 3 columns are really structure, right? The vast majority is in a building structure, and then the walls are the envelope. And I think this is really how it helps you kind of pay attention to where reductions can be made. Like, what kind of different floor systems can we be employing, and how should we be looking at building envelopes? Next. And breaking down the project's emissions, this is a way to represent them as well. This one of the city projects where you can see some of the big tickets we were asked to look at. This is the emergency services building with Diamond Schmidt Architects. Where would you make reductions? Well, you should probably start where they're greatest. So this is a representation where there's the greatest intensity of emissions in that project. Next. And in working with the project management team and the project architects, we went back and came back with some recommendations that were non-denomination changing, i.e. they would not affect, say, the grid and the overall layout of the project, this at the design development stage. And they were simply specification changes. We made some recommendations for a 30% reduction, and the team came back and said, we can do 5 of them. None of them are none of them are going to drive up cost, and none of them will also affect the construction schedule. So all to say, with just a couple weeks of analysis, we managed to shave a quarter of the emissions of this project, which was already low to start out, 800 tons equivalent of reductions. That's a good chunk. That's per capita. I think that's about 40 years, 44 years of Canadian per capita consumption. Next. So this overall way to look at this, and it's not just a number, it's, I think, just thinking like, what is 500? And this is part of the reason I started teaching around embodied carbon at the University of Toronto 2 years ago at the School of Architecture, was to help understand where it is and what's driving it right now in contemporary Toronto architecture. So 2 years ago, did a studio looking at multi-unit residential, where we looked at a range of projects recently built from, you know, as you see, low rise up to a 66-story condominium. Next slide. And the results from this are, you know, fed into what we just saw, but, you know, there's just to point out here that the low rise, as you can see, roughly half that of the mid and high rise, and that in the mid rise specifically, there's quite a bit of variation in that number. And like, you know, what's the difference between a project like SQ1 at Alex Park compared to River City 2? Like, why are they so far off, right? And where are the sources of emission? Next. And so I think, you know, in the, you know, the whole industry, just to begin to understand where this is again, that in carbon intensive structural systems, as Ryan also just alluded to with concrete, that cast in place reinforced concrete is easily the largest driver of emissions across all the projects. Low-rise projects that employed wood frame above a concrete foundation have half the embodied carbon, and that the lowest carbon mid-rise projects employed steel on hollow core structural systems, a hybrid structure, which resulted in a dramatic reduction of total volume of concrete per square meter. Next, please. So here you can see a representation of emissions across those 10 projects, radius being total emission, and then by material family. So you can see concrete clearly is king, but right next to it is aluminum and insulation, which is the next point. So envelopes, building envelopes. As an architect myself, I think this is like where all our agency is, really. And that the way that we currently kind of build and ramp our buildings is incredibly intensive. That, you know, our insulation systems that we've been using now for decades, XPS specifically, and the wall systems, the window systems we employ, aluminum extrusion-based systems, window wall, curtain wall, carry the highest embodied global warming potential of all the building materials in the study. So, you know, XPS's insulation extremely high global warming is attributed to its harmful blowing agents. Fortunately, this has now been regulated down, but not out of these products. It's still a big source. So whatever they tell you, it's better, but it's just better than bad. It's still not good. Aluminum sourcings and smelting is extremely energy intensive. You can imagine what it takes to make an extrusion and where that metal is ultimately mined and smelted and brought to the city. That these systems inherently have a high embodied carbon as a result. Next, please. And so you can see a variety of the wall sections that we saw across projects. So on the right, a kind of standard window wall assembly, one with a spandrel panel, one without, and you can see roughly 2 times the embodied carbon per elevational square meter as some of these other, you know, brick veneer systems that you would associate with, say, mid-rise projects compared to some of the high-rise. But certainly, I don't think we need to limit our thinking. I think the other kicker is when you look at the effective R value of these assemblies as well, those systems that have high embodied carbon are also very low performing, which is a problem, as a kind of double-edged problem. Next, please. Third driver is on-site parking and subgrade floor area. And I think this is where things get really interesting for everybody. Planners, architects, developers. We all know going down is expensive. Digging a big hole in the ground and filling it with cars is costly, time consuming, and it turns out incredibly intensive from an emissions perspective as well. The foundations, parking structures, below grade floor area have disproportionate impacts on embodied carbon. And so for these mid and high rise buildings, we had up to 50% of the total emissions below grade on a project. Next. So you can see in the lower rise, even these ones, just the basement, just the foundations, the cast in place wrapped in XPS. The XPS is really a big part of this. That is what you can see, that 2/3 to 90% of a project's emission is for the underground parking, just to have your parking lot below the housing. Next, please. And here are the kind of view of the mid-rise and high-rise. We're on the left, 2803 Dundas. It's the Duke condos in the Junction, built on top of an old creek. So that foundation is basically a bathtub that's, you know, perpetually pumped out. a lot of concrete just to keep those cars dry. Where right next to it is River City, in River City, where due to flood restrictions, you could not go down. So only 8%. Intelligent use of material, I would argue, not going down into the surface. Next, please. Driver 4 is also the kicker on this parking, as its dimensions, that the parking space, even when you put it down beneath a residential, is that the grid of parking is not the same of a grid of as a residential project. And to mediate these two things, you need to do some structural gymnastics through the use of transfer slabs. Next. And it's illustrated in SQ1. So I think you can see the black is the grid of the parking and the red is the grid of residential. And the entire ground floor is a meter deep, thick concrete transfer beam, simply to house 2 floors of parking below grade. And as I often say, this looks like the definition of insanity. This is clearly not the way we should be designing our buildings. Next, please. And this year we looked as a kind of counterpoint. I think there's a lot of interest and promise in mass timber. So just wanted to think about, okay, concrete was 500 a meter. What's mass timber? So we, again, next slide. Went out, got a few projects from Toronto and went a bit further afield, 2 from out in the West Coast in Oregon and Washington State, 2 here in London and 2 in Sweden. Next slide. And the results are kind of interesting. Again, a pretty big variety here. We had a variety of building heights, a couple towers, mostly commercial, 3-4 stories. Big variation here again in numbers, and a lot of it had to do with the envelope assembly. But on average, it was 443. So that's roughly 90% of what we looked at for the housing. Next. So that's not much better if you think about it. We're only 90% better with mass timber, and we're comparing commercial to residential, which isn't necessarily a fair comparison either. So I think my first observation is, just from a purely embodied carbon perspective, mass timber is not the answer. But there's a big caveat. When you look at these buildings, how do you account for the biogenic storage in them? And I think this is an argument that the industry is seeking to make, that by using wood, you're locking up carbon. And so here, even in 2 projects that have the same embodied carbon, it's not quite an apples to apples comparison if you do account for that total storage, and the net are far, far off each other. Next, please. Also, in thinking about wood and any material class, specifically geography really, really matters. The geography of not necessarily the travel distance, but where your material is ultimately sourced and processed. And so we were looking at the wood specifically, the academic tallwood tower at U of T, sourcing its wood as far away from Alberta, where those projects out west, a lot closer to the forest and the sawmill, sourcing them had a far less impact from their transportation on the actual embodied carbon of the project. Next, please. And also, it's really important to think about, if you're getting a brick or if you're getting wood or anything, the source of the ultimate production sits on a grid. I think, Ryan alluded to Ontario having a very green grid. It does, until the Ford government makes it worse. But for the time being, on just 2 days ago, Ontario's grid was 27 grams per kilowatt hour. Compare that to Alberta's at 413. So to say, well, if I'm sourcing wood cut and dried in Alberta versus Ontario, it's not the same tree. It's a different tree inherently at that point. Likewise, if you're getting brick from Brampton or if you're getting brick from Arkansas, one of the projects we had looked at, very, very different here. Orders of magnitude different, up to, I'm trying to do the math in back of my envelope here, but 24 times worse, that brick from Arkansas the other day. So when you're thinking about where your materials are coming from, this kind of makes this information is baked into the EPDs, and why generics are not necessarily a good solution. It's really important to be specific. Next slide. And also, this is why geography matters. The time value of carbon that Ryan showed in Ontario, if we think about, I'm seeing conversation around passive house here. Passive house also matters about geography. Like the argument for insulating a house, say in Alberta, is infinitely, well, it's not infinitely better. It's 20 times greater on May 5th to be doing that project in Alberta, because the grid it sits on compared to the grid it sits on in Ontario right now. We need to be thinking about these things globally. Climate is global, and geography is fundamental if we're going to tackle this correctly. Next. So the next steps we have now is that we're recommending, putting our recommendations together. This is the 3rd of 4 workshops, and as I mentioned, we'll be taking the feedback and feeding that into ultimately what goes forth as our suggestions for the TGS. Thank you.
Okay, I think it's over to me. Thanks for that, Kelly and Ryan and Lisa, for all that framing and background and the Part 3 study. I think it's really great that the Part 3 study that team did and the Part 9 study that our team did, they kind of overlapped, and it's really great to be able to sort of have that conversation between the different scales of buildings, and essentially, learn that the scope and the scale of the problem, and for sure a lot of the solutions are shared between the different sizes of buildings. Okay, so for our study, rather than the previous study for the Part 3 buildings, used life cycle assessments that the various design teams from those projects performed. For this study, we did that work. So our team took plan sets from GTHA developers. We had in total 59 different plan sets, which represented 503 as-built homes in the region. And it was a mix of single detached, semi-detached, and townhouses. So this was a pretty good sample size, and also, all the work was done using the same tool and the same methodology. So, we felt like we had a really great way to actually be comparing between these houses, because we were setting them up and measuring them in the same way. Okay, next. So we used a tool that we developed in-house called Beam. Ryan mentioned that earlier, which for a long time has been our in-house tool, but is now available publicly. So you can use Beam for sort of low and mid-rise projects, and it's available online. What we're looking at in Beam in particular, that terminology that everybody's been sharing, we're looking at the A1 to A3 emissions. So not the full life cycle of the building, but really deciding that that is where that lion's share of the emissions lie. When we're looking at materials, they're also the ones that have the most robust forms of measurement and the greatest data set that we could use. So we concentrate on what we call the material carbon emissions. And for the study, a lot like what got discussed earlier, we're looking at a fair bit of the mass of the building. So we're looking at all the structural components, all the enclosure and envelope components, and all the partitions and major finishes. So flooring, ceilings, wall coverings, cladding, insulation. So all the stuff in this drawing that's sort of checked off in green. But we are not looking at mechanical, electrical, or plumbing systems, appliances, millwork, surface finishes like paints, glues, adhesives, and none of the sort of the exterior work, the driveways, patios, anything like that. So bunch of reasons for doing that. One is that the data set for all that stuff in red isn't as good, but also the materials we have chosen represent, I think, the bulk of the emissions, and also represent the places where real options exist in order to drive emissions down. And so that, those reasons altogether make that the focus. So what we found overall is that there was an average of 42.9 tons of emissions associated with each house in the study. So if we looked across all the typologies, you can see on the far right there that the average is just under 43. But you can also see that by typology, there's a fairly big difference. Single detached houses are the highest with an average of 69 tons, and townhouses the lowest at 30 tons. And that's has a lot to do with building size. The townhouses tend to be smaller, the singles are bigger, but the singles also have, they have to wrap an entire house in an envelope, whereas townhouses have a lot of shared walls, less exterior surface area for insulation and cladding and things like that. So we can go to the next one. we actually spend more time thinking about emissions by intensity, by area, rather than total emissions. You could see there that there was a big difference if you just looked at total emissions to single families and say townhouses. So we tend to translate the results into carbon or an intensity measurement, and we can do that by either heated floor area, total floor area, or habitable area. In general, we tend to really focus on the heated area comparison, because that seems like the most salient point in terms of, for the amount of carbon that's being expended, how much of that is turning into heated space. And so you can see our average here is just over 190 kilograms of emissions per square meter of heated floor area. But you can also see that there are projects that came in quite a bit under that, and some projects that came in quite a bit higher than that. Okay, next. So essentially, this visual picks up on the average, which is 191 kilograms of emissions per square meter, with that best example. And that wasn't just a single house, that was one developer. Their whole kind of portfolio came in around that range. And at the high end, a building that was many times higher than everything else when we looked at it in intensity per square meter. Also similar to the other studies, a few categories of materials really stand out. So between concrete, insulation, and cladding, that was over 70% of the material emissions across the whole study. So if we added up all the emissions and categorize them this way, that's how it fell out. So that really just makes it obvious that if we're going to try to address this as quickly and as comprehensively as possible, that it makes sense to focus our efforts on those three high impact areas. And in fact, this is what we did for one of the homes in the study. So we chose a home, an as-built home that was at the higher end of the spectrum. So with 262 kilograms of emissions per square meter, or a total of 81 tons. And then we applied some changes. We got the best, what could be the best available concrete mix for that building regionally. We swapped out a lot of the insulation materials for cellulose insulation, which is a widely available and very low carbon option. We replaced the XPS that was wrapping a lot of the buildings, and this one in particular, with a wood fiber board continuous insulation, changed the cladding from brick to an engineered wood, and changed the flooring and drywall to the best products in their category. And that resulted in a potential 75% reduction in the carbon footprint of that building. So in the residential space, because we're not as reliant on the really high emitting categories of concrete, steel, and glass, there's actually a lot more low-hanging fruit overall in the picture of these smaller scale buildings, such that a handful of changes can make a 75% reduction. One of the interesting things is we took a house that was at the low end of the results. So, it had a much smaller carbon footprint, 33 tons instead of 81 tons to begin with. We applied the exact same set of material substitutions, and we ended up at 56.5 kilograms per square meter on that one, which is still, it's a 50% reduction. So that's great. But interestingly, the two models land fairly close to each other, 56 and 66 kilograms per square meter, which sort of indicates that if we think about the changes we can make across the board to these residential buildings, we should be able to get all the residential buildings down into that sort of 50 to 60, 70 kilograms of emissions per square meter range fairly easly. Okay, next. And I'm just going to compare that study to some other work that we've done at Builders for Climate Action, where you can sort of see in red, we've done 4 studies, one an internal study, one for Natural Resources Canada, one for the cities of Nelson and Castlegar, and then this study for the GTHA region. And you can kind of see that the results track fairly similarly in the sort of 300 to 550 kilogram range was at the high end, and we saw examples, at that rate across those studies. We saw averages ranging from sort of 150 to 190 in the middle. And we saw sort of best results getting close to, you know, 0 carbon footprint, in fact, in some of the studies, and as high at the low end as 116 in Toronto. And then we saw some outstanding results that kind of point the way to how the low-rise sector in particular could reach 0 carbon or even have net carbon storage if we kind of pick the materials right and start using a lot more biogenic and carbon storing materials. So I think the big takeaway for our team in this study, and I hope for people in this sector watching this presentation, is that the amount of low-hanging fruit here is really high. I think it's great to know that there was a GTHA builder who's just their business as usual. They were not trying to make a low carbon building. They weren't setting any goals or targets that way. Just the way they build houses, they do it, you know, profitably and repeatedly. They beat the average by 40%. So, you know, that really points to the fact that that 40% should be a pretty easy reduction across the board, because, you know, there are builders already achieving that. And out in Nelson, you know, similarly, the average was a bit lower there than in the GTHA. But again, you know, there's a builder whose business as usual practice is half of what that average was. So I think that just really points out that, you know, at least the first half of this issue, you know, getting all our low-rise residential buildings down to, you know, 40 or 50% less than they are emitting right now is, you know, it's very doable and quickly. Okay, and I think so. Our key recommendations from our study, and I hope you'll check out the study. It's available as a PDF on the Builders for Climate Action website. The sort of top recommendations were that you know, all new home designs undertake doing these material carbon emissions calculations, and that municipalities start to ask for that report as part of the permitting process, that designers and builders request EPDs from all the manufacturers you deal with. I think that those kinds of requests apply a lot of pressure to those companies, and the more of this data we have and the more product specific data we have, the better our measurements are, the better everybody knows what they're doing and what their emissions footprint really looks like. And then to, you know, really as an industry explore these immediate material substitutions that can, you know, buy that 20 to 50% reduction quickly and today, and then start kind of planning out how, you know, how we're going to get the other 50%. If we're going to hit net zero by 2050, you know, embodied carbon can't just be reduced, it has to be zero. So you know, starting to make the plans for how we're going to do that over the next few decades. Our study didn't look at ways that the buildings could have been designed differently. We just worked with the as-built drawing sets that we had, but thinking about design, the Kelly study showed that the below grade space of the large buildings had a big impact. The same goes for low-rise buildings. The less of the building that's below grade and reliant on concrete, the lower you can get the carbon footprint. And finally, we're suggesting that, you know, builders and developers in the low and mid-rise residential space, you know, declare your carbon footprint and really promote the reductions that you're making publicly. We know that a lot of Canadians really care about the climate and really want to see action taken, and that we see sort of, you know, people who want to be early movers in this space being able to benefit from identifying their house products with a greatly reduced carbon footprint. So I think that's the end of the Part 9 study, and
thanks, Chris.
Yeah, take a break now, and Ryan will sort of set up how the second half is going to work.
Yeah, thanks, Chris. We are going to take a break. We're going to just make it a short 4-minute break and start back on at the hour, and we will kick off with our breakout sessions, breakout room. So thanks everyone for that great discussion. Sorry, Chris, you're muted there. I know we would change the timing on you a couple of times, but figured we could continue any conversation here. And maybe, yeah, is there any last things anyone wants to say in the conversation before we go on? Well, actually, I guess this slide was about takeaways from Chris and I from what we heard. And if anyone else wants to jump in here, please do. But some of the main things that I heard, I went back and forth, so I didn't hear everything, but some of the main things that I heard that was really great to hear was a desire for building, not only reporting of embodied carbon for buildings, but also labeling, right? So not having the report, you know, in some file somewhere on someone's computer or on someone's desk, but on the building, so people can go and take and look and see and start the conversation. So I think that was a great, really great comment. Also, we heard some comments of, you know, let's not be so incremental. Let's not do 10% reductions, you know, every few years. Let's be aggressive and innovative and actually start designing for what we know we can and what the industry needs. So we had some good language to push us a little bit further and faster, which, you know, when it comes from industry, when it comes from you guys, it has a lot more power behind it than if some consultant has it in a report. So now we could say that, hey, the developers told us to go faster. So thanks for that. Anything else, Lisa or Kelly or Chris, you guys want to jump in and share?
I would say on our side, Doug Terry did a great job of sort of framing, you know, the approach that their business is taking to looking at embodied carbon, and you know, I would say to characterize the whole discussion, you know, we really talked about holistic approaches that, you know, embodied carbon and operational carbon, they're two pieces, but of the same, you know, puzzle. And that, you know, there are also other stackable benefits that, you know, if we can find where lots of things align, like, you know, more affordable, healthier, and lower carbon, that's, you know, those are the things that are going to enable the developer community to, you know, do it and sell it. We talked, you know, a bit about the tools, the Beam tool and the Enercan MC² tool, and people, you know, starting to use those things to understand the numbers. I'm always really bad at characterizing those discussions because I get so wrapped up in them. If anybody else from that room wants to jump in with any salient points, that would be great. Or maybe I'll capture.
Yeah, if anyone, please feel free if there is something else. But some of the a few other things, looking at my notes, I remembered one was finding an easy way to compare or to find and compare like the best class products for our region would be really helpful. So that's something that I think we might be able to recommend for TAF. That might be a great thing that they could start doing. And yeah, we heard from Jolene off the top from LS Don, who, again, from the industry, not from me, said they're finding 30% to 50% savings in carbon without impacting cost or schedule. So, you know, a lot, you know, it's not some consultant saying this is possible. It's the industry saying they're doing it already. So just to let everyone know that this is doable, and it's not going to cost you more. It's not going to impact your schedule. We just need to ask a few questions of a few key suppliers, and there's a lot of carbon we can reduce.
If I could just jump in, Ryan, too. Natalie's just who is in our room is bringing up a topic that I think is important. We didn't really discuss it, but the metrics themselves. You know, both of our studies, you kind of use this, you know, intensity per square meter. But in particular in residential buildings, thinking about, is that the right metric, or should it be also thinking about like emissions per occupant served, or how does that figure in? Because if we're just doing per square meter, you know, I could be building a very small house for 3 people that has a really high per square meter thing, but it's serving 3 people. Or I could build a monster house with a very low intensity per square meter, but it caused a lot of emissions and it did it for only 1 person. So, you know, are we sort of bundling the metrics properly? And I think, you know, that's something really for the municipalities to be thinking about, as well as, you know, the designers and builders and developers, is like, are we going to create perverse results by, you know, the metrics that we choose? And I think, you know, that's a bigger discussion, but something. Thanks, Natalie, for raising that.
Definitely, thanks. So unless there's anything else from anyone, I think at this stage we can wrap up and say thank you all for the discussion. It was a really good group of folks that we had on the call, and some really good opinions, and great to hear some of your experiences. We will be sending out an email probably next week with a link to the presentation portion, as I mentioned, and just a few quick survey questions if you don't mind answering, and probably some links as well. And yeah, I think you can find most of the presenters today on social media, on LinkedIn, and we were all sharing links to our reports and our findings and invites to future webinars and all that kind of good stuff. So you can definitely stay as involved as you like to be. And yeah, I'll just leave you with this image to keep in mind that, you know, there's a lot we can reduce. So yeah, unless anyone else has anything to say, I will say thank you all, and let's stay engaged, and let's lower our embodied carbon.